This tutorial is about viewing the outputs in RAPT. We're going to use the file that we created in the tutorial introductory RAPT run. So I'll open that now. In that RAPT run, we had already inputted all of our details for the frame, our load cases, and our reinforcement. And we are now going to output. Once we click output, RAPT does the calculations and produces these design outputs. You can also click this button here, which is calculate results. If you think there might be an error in some of your logic, you can click logic, and that will give you some of the output warnings and or errors that you have in your design. And if RAPT ever gives you errors showing like that, and it often does if you are putting in PT tendons and there's a problem with reverse curvature, it'll come up with these warnings and errors, and you just click that again to remove them to show this graphics again. So having done the calculations, or to get the calculations done, we click on output. RAPT has done the calculations, and we now go to our output. Here we go. So the first thing we see are bending moments. RAPT provides bending moments for each individual load case and for the load combinations. As an example, I'll show you the ultimate design bending moment diagram, and it's an envelope case which includes pattern loading, and that gives you the upper and lower bound bending moments. If you click on the mouse at any point in the graph, it will give you a distance to grid in this zone here. So you'll see as I click, that changes the distance to grid. And if you click on any of these items here, it gives you the value at that location. If you want to see more information, you can click on I, show extra information, and that'll give you the shear and moment values at each of those locations as you change and cycle through the frame. You can also zoom on to any part of the graph if you want to see more detail. Here it won't make much difference because it's not very complicated, but I just double click on the graph and it zooms into that span. Double click again and that zooms back out. If we go to the text view, this shows the same information but in text format, and you can see that it shows you for each span the moment and shear at each location, and these are each of the critical locations along the span. I should also mention that in the graphics it'll give you the worst case sagging moment, and then the the bending moments at the face of the column, and shear at the face of the column plus 0.8D or 0.7D, depending on what your code requires for the critical section. Okay, that's bending moments. Then RAPT shows you what design has been done. Now you may remember that back in our input, we have reinforcement, we had design zones, and we had user-defined reinforcement. In this user-defined reinforcement, we had put in all the reinforcement that RAPT had designed for us, and I'm going to remove this bottom reinforcement, or some of this bottom reinforcement, so that you get a feel for what RAPT does in the outputs. So in the top reinforcement, I'm going to remove these design bars here. Delete that bar. Delete that bar. Okay, we go to output and we go to flexural design. Now, with all outputs, there is a text output and a graphics output. Both show pretty much the same thing. Let's start with reinforcement. In the reinforcement text output, RAPT shows you top design 1, bottom design 1. Top design means this is the reinforcement that RAPT is adding to the design. Bottom design 1 means this is the reinforcement that RAPT is adding to the design. Top 1, top 2, bottom 1, bottom 2 is user-defined reinforcement. This reinforcement is all the reinforcement required for flexural, shear, and crack control. If we go to Ultimate Design, the text box, we have a number of columns here. Again, we have the critical locations, we have our design moment, we have our minimum moment, which is based on 1.2 times the cracking moment. We have an initial condition. The initial condition is the capacity of the section based on the user-defined reinforcement only. It gives you a capacity and then the ductility ratio, which is your neutral axis position, as a ratio of the effective depth. And in this case, you can see that our minimum moment is, our capacity is higher than our design moment, and so there is nothing added to the reinforcement. There's no added reinforcement for flexure in this line. So the final design condition is the same as the initial design condition. It also gives you the final design, the maximum strain ratio of the bar, which is just the percentage of the maximum strain limit. In this example, we are using 0.05 as the maximum strain limit. This is the reinforcement that is added to meet flexural demand, as opposed to the reinforcement that was shown here, which included reinforcement to meet flexural, shear, and crack control requirements. So this reinforcement, and we'll see at the very bottom because we took those bars at the top on the right-hand side out, RAPT has added reinforcement for flexure on the top. You can see if we take one of these lines here that the reinforcement in the final condition is 297 to meet the design moment of 277. In some locations, the minimum moment governs. So here at position 1712 millimeters, into span 5, we have 148 kilonewton meters being the minimum moment, and the initial condition being 0 because we had no reinforcement there. RAPT has added reinforcement to meet that minimum requirement, and that is the final condition. That is ultimate output in text, and we can see the same thing in graphics. The graphics combines a few things. So in the top here, RAPT is showing how much reinforcement it has added in the span. So this is just reinforcement that RAPT has added, not user-defined reinforcement. And if we click these buttons here, we can see what each of these values mean. So the total reinforcement that RAPT has added at location 7152, you can see that at the very bottom left of the screen, distance to grid 4, 7152, and also up here, 7152. It has added 1852 millimeters total reinforcement, which is the reinforcement required for shear, ultimate flexure, and crack control. If we just want to know the reinforcement added for flexure, we can click top ultimate, and that just shows the reinforcement for flexure. So you can see that RAPT has added reinforcement for the offset of the bending moment diagram, which is the tension force required for shear. Down the bottom here, there is minimum top and minimum bottom. Those are reinforcement requirements for any basically code requirements, often required for in some codes where you've got unbonded pre-stress. Down here is your capacity. So the green line is the minimum line, the black line is the design moment, and the initial design is in orange, which is not that apparent because in most cases the initial design matches the final design because they were based on our user-defined reinforcement, except here where initial design at the hogging locations is 0 because we took that reinforcement out. So in these locations, the final design ends up being very closely matching the design moment and then also matching the minimum reinforcement requirements. And you can see the difference here in terms of the what RAPT is assuming as the reinforcement for its design. Here it's including all the reinforcement that was put in as user-defined reinforcement, and the capacity is right across here, extending up as the bar would, because it extends that distance. Whereas here, RAPT is just putting in the areas of reinforcement required at each design location. And once you put a bar in, you can't get a bar to match that capacity line, so you end up having a straight line across there. RAPT calculates deflections based on this reinforcement, and I'll talk more on that later. This bottom graph here shows your neutral axis depth as a function of your effective depth, so your value Ku, which is a measure of your ductility. Sometimes RAPT will adjust reinforcement or add compression reinforcement to bring your neutral axis depth down to an acceptable limit. That acceptable limit is defined in your input under design data, ultimate, and here neutral axis depth for ductility. That's often defined in the code in any case. Back to our output. If we click on the information dialog, and again, I think I said this before, but if you double click on any part of the graph, RAPT will zoom in so you can see more detail. If we click on the information dialog, RAPT will give you more detail, or the same information, but all of it in one page. So for this design location, RAPT is telling you we need a total of 2,474 millimeters squared, of which 2,300 is for flexure and 160 is for service. And there may be some locations where some is also required. Sorry, I said service, I meant shear, but it is required for service here, so for crack control. But there are some areas where it's required for shear and for crack control. Okay, that's it for ultimate. We'll now look at service output. In the service output, we have a service moment. Your service moment is your combination load case for serviceability, which is this load case here, short-term service. And it also includes your post-tensioning effects, P times E, plus your secondary moments from bending. And that's what that moment there is applied to your uncracked section to calculate your gross stresses. And the MS mod is the same as M service, but it doesn't include the P times E, or your axial force times your eccentricity for the post-tensioning, because that post-tensioning force and your eccentricity is part of the internal resistance in the cracked calculation. So this MS mod is used for cracked calculations. Gross concrete stress, this is basically uncracked results. You have your P on A, your average pre-stress. You have your top stress and your bottom stress. You have your second moment of area, uncracked, and then you have your crack section results. RAPT will give you your compressive stress. So this would be at the bottom of the section in a hogging zone and the top of a section in a sagging zone. It'll give you your neutral axis depth in millimeters. It'll give you your tension stress change, which is the worst case tension stress change in the reinforcement. In a reinforced section, that's just calculated from when the beam is unloaded to when it is loaded with all loads, self-weight, SDL and live load, with the combination case for service for serviceability. If you have a post-tension member or pre-tension member, then this number here is calculated not from the unloaded condition, but from the decompression moment. So in other words, when the beam is under load and just at the point at which the tensile face has a stress of 0, that bending moment is, or the stress in the steel at that bending moment is compared to the stress in the steel when the beam is fully loaded under SLS loads, and that is the tension stress change for post-tension members. Extra tension reinforcement is added if RAPT cannot calculate a maximum spacing or maximum bar size that will satisfy crack control. So there are some examples. If I go down towards the bottom, you can see that RAPT has added reinforcement for crack control, and the reason it's done that is it's come up with a bar spacing which is less than the minimum we've set in our input. So if I go back to input and I go to reinforcement general, we said our minimum bar spacing was 60. We go to our output and RAPT says, well, in order to achieve your crack control, and remember crack control, unless you've defined it specifically, is typically 0.3 millimeters for reinforced concrete members and 0.2 millimeters for post-tension members. So to achieve 0.3 millimeters, RAPT will look at the spacings and bar sizes recommended in the code, and it'll spit those back out. Now, if I go back down here, the maximum spacing is 58, which is less than our minimum of 60. So RAPT will add reinforcement to achieve crack control. These bar sizes and bar spacings are not put into the reinforcement layout by RAPT. These are just guidelines for you to achieve crack control, so you must detail accordingly. This is your cracked second moment of area, and then RAPT will calculate your effective moment of inertia for deflection using a combination of the uncracked and cracked inertias, and it does that using the method you put or that you specify in design data, and in deflection you can put in your tension stiffening approach. RAPT defaults to the modified concrete tensile modulus method, and there's more information on that in the help if you want it. Back to output, we have finally we have our strain in the top face and the strain in the bottom face in sagging, and then opposite in hogging. We have the same information in the graphics output. So here we have, where we have sagging, we have compression in the top of the beam and gross stress at the top of the beam. They are compressive stresses. Stresses in RAPT are positive. Compressive stresses are positive. Negative stresses are tensile. And then we also can look at this from the section, which is a little bit more intuitive. So we click that, and we can see that at the top of the section it is in compression, and this is uncracked, of 3.64 MPa. At the bottom it's in tension 5.84 megapascals. So and then in cracked, when it's cracked, it has compression stress of 7.57 MPa, with the tension stress being 266 MPa about this location here. And you can move that wherever you like to see how the section changes. This is the typical serviceability combination, and this is the reversal. So in other words, the under pattern loading, what the minimums would be as well. Minimum sagging, maximum hogging. Okay, we've got permanent and characteristic service. They are Eurocode equivalents or similar outputs to service, but for the purposes of calculating crack control. So the outputs are the same, but they are just used to calculate crack control reinforcement. Then we have shear design. So we have an output here, a text output, and I'll run through each of these columns. This is your shear force. This is your bending moment for that shear force, and that shear force is your worst case shear force at each of those locations. PV is your post-tensioning force, the vertical component. That vertical component is either beneficial or adverse depending on the direction of the tendon. D is your effective depth of your tensile reinforcement, so from your compressive face to the centroid of your tensile steel. Remember that tensile steel is defined as the tension steel in the lower half of the section. AST is any reinforcement that RAPT has added for shear calculations. It's not the total AST used in the calculation, it's just the AST that RAPT has added for flexure and is used in the calculation of shear capacity. So in other words, in other areas where it has 0, there is user-defined reinforcement that RAPT is using in the calculation, but not shown here. BV is the effective width of the section. Phi VU is the capacity of the section concrete alone. Phi VU max is the maximum capacity of the section in shear, and that's limited by your web shear crushing failure. Phi VU min is the capacity of the section with minimum steel required. Phi VUS is the contribution made by the steel, the rest of it made up by the concrete. Theta is the angle which RAPT is using to calculate your shear capacity. ASV on S is your millimeter squared per millimeter, so it's your shear reinforcing requirements. The equivalent of this in terms of shear legs are shown here. So these 2 legs are 10, 4 legs are 10, 6 legs are 10. They are defined back in input under under general reinforcement, and there our shear option 1, 2, and 3 are shown. So we can change those options as we like. And then RAPT will tell us what spacing is required for each of those options to meet your shear force demand. Minimum number of legs. This is the minimum number of legs required by the code, and it's typically your minimum transverse base or dependent on your minimum transverse spacing of your shear legs. And then this here, minimum legs R10, is the minimum spacing for the minimum number of legs. In other words, you need 3 legs at 199 millimeters or 200 millimeter spacing if you want to meet your shear design, your shear force demand. The same thing is produced, or the same information is shown in graphics. Here are your shear leg spacings for each of your options. Here are the minimum number of legs, with those legs shown on the secondary y-axis, and this is your spacing for 3 legs, for minimum legs. So underneath that we have our shear capacity. So we have our concrete capacity, then we have our minimum capacity with shear steel. Here we have half concrete capacity, which used to be an AS 3600 limit on whether or not you needed shear reinforcement. That's now KS times concrete capacity for AS 3600, and that will be updated in the next release. Finally, we have our applied force, and that is shear capacity. Lastly, we have punching shear. If you want to know what each of these tables, each of these things means, again, you just hit F1 when you're here, and RAPT will give you all the details for the each of those columns. But effectively, this punching shear calculation will tell you your torsional shear requirements, and then your shear requirements for punching shear. Now moving on to deflections. We go to deflections. Now deflections are more easily looked at graphics, so we'll skip the text view. Deflections are shown in 4 basic quantities. One is at transfer on final stress. Then it looks at short-term deflection being based on your combination case for deflection under short-term. You then have incremental and long-term deflection. Long-term deflection, again we go back to our load cases, long-term deflection is based on your permanent deflection load case based on long-term properties minus your permanent deflection load case based on short-term properties. That gives you your long-term component of deflection. We add to that short-term deflection, and that gives us our total long-term deflection shown here. Incremental deflection is long-term deflection minus our initial deflection, which is our self-weight plus our initial dead load. For each of these cases, we are showing our even spans loaded, odd spans loaded, and then all spans loaded. For long-term deflection, we show our total deflection and then our deflection relative to the column, the tops of the columns. So in this case here, the column has shortened by 0.2 millimeters. So the, well, assuming it's 0.2 millimeters both sides. So the deflection relative to the tops of the columns is 0.2 millimeters less than this total deflection amount. And the span to deflection ratios are based on this number here, 21.5. Finally, I should mention that RAPT is calculating deflection based on the minimum reinforcement it has designed. So if we go back to our output for flexural design, ultimate, I'll go to graphics. This reinforcement here, top total, is the minimum reinforcement RAPT has required for each of shear, flexure, and crack control. That is the reinforcement that RAPT is basing its deflection on. So deflection here is based on that reinforcement. Those reinforcing amounts. Now those reinforcing amounts could be satisfied with any combination of bars. RAPT suggests one particular solution, one of many, in this output here, reinforcement layout graphics. This bar arrangement is one solution, and that solution provides more reinforcement in some locations than is required by the minimum requirements set out in this, set out here. So if we have more reinforcement that's required, RAPT does not calculate deflections based on this additional reinforcement here. If you want RAPT to reflect that, and you can see this is RAPT added reinforcement because it doesn't have brackets around it. Brackets means it's user-defined reinforcement. No brackets means it's RAPT designed reinforcement. If you want RAPT to calculate deflection based on total reinforcing, then you go back to input, you go to reinforcing, user-defined, and you click this button here which says insert design reinforcement pattern, and RAPT will add the reinforcement that it designed. If we go back to output, you'll see that all the reinforcement here is all in brackets, which means it's all user-defined, and RAPT will then calculate your deflection based on that reinforcement layout. And that's it for output.